Hello everybody, in this video we're going to continue building on the previous example of calculating the Laplace transform for various functions. So let's take a look at the Laplace transform for e to the at, where a is just some real number. Okay, so if we think about our existence theorem, the two conditions we need for this thing to exist. The first condition, f needs to be piecewise continuous on some interval, and we can see e is actually continuous, so that's sufficient. So we can just make a note here that f is piecewise continuous. And this is true for any interval from 0 to a. The second condition is that the f needs to be, what was the wording we used? It's the exponential order. There you go. The exponential order is our function of exponential order. Let's check it. F of t, well, this is e to the at. Is this bounded by some exponential function k e to the ct? Well, yes, of course, for k equal to 1, c equal to a, where c is any number bigger than or equal to 0. So the existence theorem tells us the Laplace transform exists for s bigger than c, and in this case c is a. Okay, so we know it exists. Let's have a go at calculating it. So the definition of the Laplace transform for e to the power at is the integral from 0 to infinity of e at, that's our little function, little ft, times by e to the minus st, integrated over t. So in here we should look to simplify. Let's do that next. This is just the same as a minus s in a bracket times t integrated over t. Well, how about this infinity in the integral limit we saw before? This is just the same as taking some limit. I'm going to use big X again. So the limit, the 0 goes to infinity of this integral, as big X goes to infinity, of course. Okay, so next, let's do the integration. So integrate e some constant, which is a minus s, times t. Well, this is the same as e a minus s in a bracket times t over a minus s. And we're going to evaluate this between 0 and big X, remembering these are values of t. Okay, so let's put those in. We end up with e to a minus s x over a minus s. And if we put 0 in, we get e to the power 0, which is 1, over a minus s. Of course, we subtract. Now, dealing with the limit as big X goes to infinity, that deals with the infinity symbol on the integral. Well, we can see here we have the a minus s, and we know s is bigger than a. So if s is bigger than a minus s is negative. That is very good news, because as x gets very big, the power of e gets very negative, a very large negative number, which of course gets closer and closer to 0. Okay, so what we have is 0 at the top of the fraction, and the second term just stays as it is. This first term is just 0, and I'm going to rewrite that as 1 over s take away a, and there you go. We have our answer. The Laplace integral of e to the at, that is this one here, is equal to 1 over s minus a, where a is just a constant. Okay, so we can think about some different values of a here. If you think about a as being maybe 1, so the Laplace transform of e to the t is 1 divided by s take away 1. We could think about a as being 2, so the Laplace transform of e to the 2t, 1 over s take away 2. 3 is the same, 4 the same. We can change any number and we get an idea, we get the exact answer in fact of the Laplace transform.